So many of us use them every single day. I'm talking about large language models, or LLMs. And they can feel, well, kind of like magic, right? They write poetry, they spit out code, they can even just chat with us. But behind that simple, clean text box, there's an operation on a scale that's almost impossible to wrap your head around. So let's pull back the curtain and really uncover the machinery that's powering all this magic.
So what's really happening inside an AI's brain when it thinks? It's tempting to picture this little genius sitting inside the computer pulling levers. But the reality? Oh, it's so much more interesting. It all boils down to two things: a whole lot of math, and massive, and I mean massive, hardware.
Okay, so first things first, we've got to peel back all the layers of science fiction to get to what an LLM actually is. Let's just forget about artificial consciousness for a minute. The truth? It's a giant statistical engine. That's it.
Now, I know that sounds super complicated, but stick with me. At its very core, an LLM is just a really, really complex math function. And it has one single job. Look at a bunch of words in a row, and then guess the probability of what the very next word should be. That's it. That's the whole magic trick, right there.
But here's a really crucial point. The model isn't just some giant copy and paste machine, memorizing sentences from the internet and spitting them back out. If it did that, it would be totally useless, right? No, instead, it's learning the deep underlying statistical patterns of language. We're talking grammar, facts, logic, even writing style, all by crunching through trillions of words.
Okay, so to learn all those patterns, the model has to tune an absolutely incredible number of internal knobs. Think of it like an old radio with billions of dials. These are officially called parameters. And each one of these little knobs holds a tiny, tiny piece of information about language. So here's a question for you. Any guesses how many knobs we're talking about for a famous model like, say, GPT-3?
175 billion. Just let that number sink in for a second. Every single one of those 175 billion parameters is a number that gets tweaked and fine-tuned millions upon millions of times during training. This is where all the model's knowledge actually lives.
And guess what? The trend is only going up and fast. For GPT-4, that number is estimated to be over 1 trillion. Yeah, a trillion. This right here, this exponential growth is the #1 reason why the need for massive data centers is just exploding. Because more parameters means more nuance, more capability, and a whole lot more number crunching.
All right, so we've got a trillion of these knobs to tune. How on earth does that actually happen? Well, let's imagine an assembly line. We're going to follow one single sentence as it makes its way through this massive machine.
So here's the roadmap for our little sentence. First, it gets chopped up and turned into numbers. Then, it goes through the absolute core of the model, the engine room. The model then makes a prediction. And then, and this is the most important part, it learns from its mistakes by adjusting every single one of those trillion parameters. It's a constant feedback loop.
Step 1. Tokenization. Look, the model can't read words the way you and I do, so the first thing it does is break our sentence down into the smallest possible meaningful chunks. We call these tokens. This is how it understands grammar and word roots. For example, it sees the word playing as two separate ideas, the root play and the suffix ing. Pretty clever, right? Okay, next up, embedding. Each one of those tokens now gets translated into the only language the computer truly understands, math. It gets converted into a really long list of numbers, which we call a vector. You can think of this vector as a kind of coordinate that pinpoints the token's meaning in a huge, abstract idea space. So words with similar meanings, they'll have very similar vectors. And a whole sentence, well, that just becomes a big grid of numbers, a matrix, all ready for the heavy-duty processing.
And where does all that processing happen? Right here. We're now heading deep inside the transformer. Seriously, think of this as the engine room of the whole operation. This is where the magic and the most computationally intensive work really happens.
This engine is built by stacking a bunch of identical blocks, kind of like Legos, and each block has a few key parts. The absolute star of the show is something called self-attention. That's how the model figures out how all the words in a sentence relate to each other. The other parts are there to help process all that information and just keep the whole learning process stable. A really big model can have almost 100 of these blocks stacked one on top of the other.
So if there's one thing to remember, it's this. Self-attention is the secret sauce that gives the model context. For instance, if it sees the sentence, "The bee landed on the flower because it wanted nectar," self-attention is what helps the model figure out that it refers to the bee and not the flower. And it does this by calculating an influence score between every single word and every other word in the sentence.
So how does that actually work? Well, we're not going to get bogged down in the crazy math, but just think of it like this. For every single word, the model is basically asking, hey, how relevant is every other word in this sentence to me? It then calculates a score for each relationship and uses all those scores to build a brand new, much richer understanding of each word based on its specific context. And it does this millions and millions of times.
Okay, so we've looked at the math, we've peeked at the architecture, now for the billion-dollar question. Why does all of this require a building the size of a city block that's just packed with computers? It's time to connect all this abstract math to the cold, hard metal.
And it really boils down to two major physical roadblocks. The first one is just the absolutely insane amount of computation that's needed. The numbers here, they're truly staggering. So remember that self-attention calculation we talked about? Well, imagine doing that for every single token in the training data. Now repeat that across all 96 layers of the model. And then repeat that entire process millions of times over for each training step. You end up with quadrillions, that's quadrillions with a Q, of mathematical operations.
And there is no single computer on planet Earth that can handle that kind of load. The only way to do that many calculations in any kind of reasonable time frame is to get thousands of specialized processors, GPUs, all working together in parallel 24/7 for months straight.
But raw processing speed, that's only half the battle. The other major bottleneck is memory. You have to be able to hold the entire trillion-parameter model and all of its ongoing calculations in active memory all at once. And these memory needs are just as mind-boggling. A trillion-parameter model needs about 16 terabytes of super-fast memory just to exist. But wait, there's more. You need to double that for something called gradients, and then you have to double it again for the optimizer states. All told, you're looking at over 50 terabytes of active memory. To put that in perspective, the beefiest GPU on the market today has less than 1/10 of a terabyte. It's not even close.
And the demands just keep piling up. All those thousands of GPUs have to constantly talk to each other with almost zero delay, which means you need ridiculously fast networking. Then there's power. They consume megawatts of it. We're literally talking enough to power a small town, which generates a ton of heat that needs massive industrial-scale cooling. Oh, and you also need petabytes of storage for all the training data and model checkpoints. It's a lot. So let's just put this all together, right? It's a total chain reaction of scale. To learn human patterns, you need a massive data set. To store all that learning, you need billions or even trillions of parameters. To train those parameters, you need insane GPU compute for quadrillions of operations. And to make all that happen, you need terabytes of memory, an ultra-fast network, and a megawatt-scale facility to power and cool the whole thing. See how it all connects? Which brings us to the final and most crucial takeaway of this whole thing. The reason LLMs need these giant data centers isn't because they're some magical thinking AI. It's because when you strip everything else away, they are simply giant statistical engines. And the language they speak isn't English or Python, it's massive, incredibly resource-hungry linear algebra.